Hello everybody, and welcome to the presentation for the hot of the press paper Parallel Multi-Objective Optimization for Expensive and Inexpensive Objectives and Constraints. My name is Ruud Winter and this is a joint work between me, Bas Milatz, Julian Blank, Nicky van Stijn, Thomas Bäck and Kalyanmoy Deb. So let's go straight to the problem statement. The problem at hand is that we have a constrained multi-objective optimization problem that is defined with k objectives that can be either expensive or inexpensive, m constraints that can also be expensive or inexpensive, and d decision variables. Usually we would use Bayesian optimization algorithms to optimize such a problem. However, how do you deal with if one of the function is being inexpensive? And usually what is also a problem in Bayesian optimization algorithms is that only one solution per iteration is proposed, which makes hardware exploitation and commercial licenses exploitation difficult. So I came up with a solution. The proposed solution is the IOC Sama-Cobra algorithm, in which you can define if an objective is cheap or if an objective function is expensive. You can do the same for the constraints. The constraints can also be denoted as cheap or expensive. The IOC Sama-Cobra algorithm stands for Inexpensive Objectives and Constraints, Self-Adaptive Multi-Objective Constraint Optimization Algorithm by using radial basis function approximations. So for the expensive objectives and constraints, the radial basis function approximations will be used, while you can also use the inexpensive objectives and constraints directly into the algorithm. So instead of using a surrogate for the inexpensive objectives and constraints, you can directly exploit them. And this is what you will see in the pseudocode. So let's now go to how a surrogate is fitted. You can see here an example of a cubic radial basis function fit where we try to fit the blue dashed line. You see that every iteration, the more training points are added, the more accurate the prediction will become. Then after you have fitted all the surrogates, you can optimize an acquisition function or infill criteria. The acquisition function that is usually used is the hypervolume performance indicator. The hypervolume performance indicator computes how much hypervolume is added if a solution would be evaluated. And that volume is being predicted based on the surrogate predictions for the two objectives. You can then compare a solution that would contribute the green volume of hypervolume or the red volume of hypervolume. And in this case, you would obviously choose the solution that contributes the most hypervolume. You can do this for one solution at a time, but you can also do this for multiple solutions at a time. And you can make predictions for the objectives based on the surrogates, but if you have the inexpensive objective or inexpensive constraint, you can directly use that to propose, to predict or to evaluate how much hypervolume this solution would add to the hypervolume. And then based on this, on multiple solutions simultaneously, you can also predict how much hypervolume a set of solutions contribute to the hypervolume instead of only one solution at a time. By checking the set of hypervolume contribution of multiple solutions simultaneously, you automatically find solutions that are more diverse. And that's what you see here with the green boxes and the red boxes. Because the red boxes have a lot of overlap, the green solution set will be preferred over the red solution set. So this infill criteria can be optimized with the Cobra optimization algorithm that uses a trust region and iteratively adjusts this trust region to find optimal solutions. So I tested this optimization algorithm on a set of benchmark functions. I tested on 22 test functions, and all these test functions have different number of objectives, different number of constraints, and different number of decision variables. I experimented with the multi-point acquisition function and with the inexpensiveness that can be defined in the objectives and constraints. I compared the IOC Sama-Cobra algorithm with the original Sama-Cobra algorithm that assumes that all objectives and constraints are expensive. I also compared to the surrogate-assisted NSGA2 algorithm and the inexpensive constraint surrogate-assisted NSGA2 algorithm. So to fairly be able to compare it, we assumed that the constraints in all these test functions are inexpensive, while the objectives are expensive. Um, Based on the benchmark results, we can see that based on the hypervolume indicator and the IGD plus indicator, that the IOC Sama-Cobra algorithm usually gets the highest rank according to the Friedman rank test. And according to the Wilken rank uh, test, you can also see that the IOC Sama-Cobra usually outperforms the other algorithms. This is again confirmed with the empirical cumulative distribution function that aggregates all the results and plots this in some kind of convergence plot. What is also interesting to see here is that independent of the base algorithm, exploiting the inexpensiveness is beneficial. I applied this on a practical problem where we optimized the ship design problem where we wanted to maximize the cargo hold volume and the damage stability criteria. So we want to maximize that by maximizing the cargo hold and maximizing the attained index that stands for damage stability criteria. And here we can see that the IC Sama-Cobra algorithm outperforms the circuit assisted NSGA2 algorithm. It converges faster, and the Pareto front approximation is much better. So in conclusion, try the IOC Sama-Cobra algorithm on your problem because the code is public, and let me know your experiments. Please also join my talk in the UMIS finals to learn more about the application, or join my talk in industrial applications of meta-heuristics to learn more about single objective optimization with constraints. Once again, my name is Ruud Winter, and I hope you liked my talk.